think it's a multi-trillion-dollar economy, right? I think this is going to be the most important and consequential technology we've ever invented.
Welcome back to ModCons. Today I'm joined by Dr. Adrian Woolfson. Dr. Adrian Woolfson is the CEO and co-founder of Genyro, a San Francisco-based biotech startup. Although that description doesn't quite do it justice. Dr. Wolfson studied medicine at Balliol College, Oxford, and undertook his doctoral and postdoctoral work on natural and artificial CD1 genes and protein folding at the MRC Laboratory of Molecular Biology in Cambridge. He has been a fellow at the Wellcome Trust, Darwin College, Cambridge, and global clinical lead for early and late stage hematology at Pfizer in New York. He's also just published his third book on the future of species, this great book here, a Financial Times Book of the Week. And we are absolutely delighted to have him with us today on ModCons. Dr. Woolfson, thank you so much for joining me today.
Jamila, thank you very much for having me on your show. It's great to be on.
Thank you. So, Dr. Wolfson, I'm going to call you Adrian, if that's okay.
Yes, it is.
Amazing. So you've had such an illustrious career that I couldn't fit it all into the intro. How did you end up here? What led you into the world of science?
Yeah, when I was about 6 years old, I was lying in bed and I was ill with a temperature. And my dad came to speak to me. He said, Adrian, the human body's the most complex machine in the world. And I thought, oh gosh, really? What, more than a washing machine or a television, And I think that's really what got me kind of intrigued about biology, this idea of the human body as a machine that could go wrong and then maybe could be fixed. So I think that sort of idea subconsciously got implanted in my mind at a young age, and the rest of my life has been about working through that idea and seeing what I could do about it.
That's incredible. So it's great that you started so young. So you're now the CEO and co-founder of Genyro. Is that how you say it, Genyro?
It's actually Genyro, but there is some
Genyro.
there is some variation in how it's pronounced. So I'll allow you to,
Thank you.
find your own happy way to
My
do
own
it.
way. So it
Yeah.
is a biotech startup based in San Francisco. Could you tell us a bit more about what you guys do?
Yes, so I've got two key co-founders. One is Brian He, who's at the Arc Institute in Stanford, and he's the sort of guru of using artificial intelligence to design DNA up to the scale of whole genomes. And my other key, inventor, co-founder is a guy called Kai-Hang Wang, who's based at Caltech in Los Angeles. And he was also at my old lab in Cambridge, although we didn't overlap. And he's invented a method called Sidewinder for building DNA at scale. Think of it as a kind of laser printer for printing out DNA. And so my company, Genyro, takes the inventions from both of these individuals and puts them in one home, which is Genyro. And the other co-founder, a guy called Noah Robinson, is a sort of brilliant experimentalist who also helped develop Sidewinder. So the four of us were the co-founders, and together we have the technological capability both to write genomes and to design them. So we're like the kind of architects, if you like, and the construction company. So it's the kind of full, capability in one place. But we're talking about here building life, not buildings.
I love that. I love that. And so, in your book, on the future of species, everyone go and guess it. You talk about, being able to build species from, or the possibility of being able to build them. You discuss the importance of synthetic biology, also known as generative biology. And you mentioned that through the convergence of AI, DNA could be designed and built at scale, and that eventually, will no longer be observing life, but being able to actually create life. You call this artificial biological intelligence, or a form of it, artificial biological intelligence. Could you tell us a bit more about that theory and what you're thinking of?
Yes, yeah. The term artificial biological intelligence is one that I coined myself, and it was obviously based upon artificial general intelligence, which is, AI's eventual ability to function literally at the level of humans and beyond. Actually, I think we're not far off that personally. Myself, I have honestly amazing conversations with ChatGPT every night, which are as good or better than most humans, right? So I think it's already performing pretty well, right? And then artificial superintelligence is when we go beyond humans, right? But I felt that when you apply AI to biology, you do something remarkable and totally new, which is you use AI to understand the grammatical rules of how biological systems are constructed and function, and also, how they might potentially be redesigned. And I thought that deserved its own phrase. So I thought artificial biological intelligence was a good way of kind of capturing that concept. And it has four components, actually, the way I define it, because I published a paper on it, right? One is the ability to look at a sequence and predict what it does. So, for example, if I'd never seen a giraffe before, and you threw me the genome sequence of a giraffe and said, what does this make? I'd immediately be able to say a giraffe, right? Or we may not have called it a giraffe, but a giraffe-like creature with a long neck and its specific coloration and that behaves in a certain way, et cetera, right? So that's the predictive component. And that also implies that there may be species that have never existed, right? That if you designed a genome sequence for them, would be able to tell you what they did. And that's the critical predictive component, right? And then there's the ability to uh, actually generate genomes of things that achieve particular aims. Like if you said to me, "Hey, Adrian, give me the genome sequence of a cross between a zebra and a flamingo, or a rhinoceros and a flamingo, which could be called a flaminoceros, let's say, right? And I'd say, yeah, sure, here it is, Jamila, or no, that's not computable. There is no such genome sequence that can achieve that. Or if you said, hey, give me the genome sequence of bacteria that can destroy microplastics or rewrite my chromosome 6 to get rid of diabetes, that's the kind of generative component. Then you've got the constructive component, which is the ability to physically build those genomes. And then you've got what I call the kind of boot up component, which is having built that genome, you need to then activate it and make it into a living thing. So those are the four components of what I've called ABI. It's the prediction, generation, or recognition, prediction, generation, construction, boot up. If you can do all of those things, you're doing ABI.
Amazing. It sounds very complex, which is great. But in your book, you also say, there is a danger of it being in the wrong hands, and you suggest some guiding principles on how we can assure that ABI is used responsibly and for common good. How easy would its malpractice be to detect? And how realistic would it be to prevent? We see the lengths some nations feel they have to go to administer things like nuclear disarmament, and also how quickly a virus like COVID could spread. How easy is it to actually keep this under control?
So this new technology is really represents a phase change in the history of life on Earth. We need to realize that this is something totally new. We've moved from Darwinian evolution into a post-Darwinian age, where we can actually contemplate authoring life from first principles. And with that new competence comes huge responsibility. We need to learn how to do this safely, wisely, ethically, equitably, and as you say, in a way that benefits society. Um, and in order to do that, we need to work out an appropriate governance system, right? And that's not trivial. And I think there needs to be some kind of, you talked about nuclear power, right? There needs to be some kind of international, like the sort of anti-proliferation type of equivalent, if you like, for biological design and construction, just to keep an eye on what's being done where and how it's being done, and to align on international guidelines and what's acceptable and what isn't. And obviously, then at the national level, there also needs to be governance. It's not going to be easy. In fact, you can be almost certain that we won't get international alignment. We can't even get national alignment on most things, right? But that doesn't mean to say that we shouldn't be trying to do that, right? And it's actually essential that we do. Your other question was, how would we know that somebody had violated this? And well, in some instances, it would be obvious. For example, actually, only yesterday, I saw a company announcing that it was launching into a program of responsible germline gene editing. Germline means inherited gene editing. And so what my response to that, which I posted, was, the words responsible and germline gene editing don't actually sit well in the same sentence, right? So even with things like gene editing, we can see that for some reason, this company doesn't seem to recall that there's a global moratorium on germline gene editing. We've already seen what happened when that was done in China, right? Unfortunately, there isn't actually any specific governance which is legally enforceable to control that as of today. So when we say there's a global moratorium, well, actually, there isn't really. It's a kind of opinion or a viewpoint, but it's not enforceable, right? So at some point, we are going to have to try and, build this into law. And we need to do that in a way which doesn't prohibit scientific freedom, because at the end of the day, scientists need to be free to imagine, right? And all technologies are dual use. Fire is dual use, the wheel is dual use, right? But so we need to appreciate that all technologies are dual use, and we can't prevent technological progress. I mean, AI is an extraordinary technology, but it looks like it's going to put half the world out of a job, right? But we're not going to stop doing AI because of that, right? Because there are obviously huge upsides. But what we're going to need to do is to learn how to address the consequences. And we also need to preempt them, because whereas, the Industrial Revolution occurred over decades, technologies like AI and generative biology have an immediate disruptive effect. And we don't have much time to adapt to them, so it's a rate of change, a pace of change, which is quite unprecedented in human history. And we can't kind of respond post hoc. We need to actually preempt these things and create a regulatory and environment and appropriate governance that can receive these anticipated technologies and be ready for them, which frankly we're not doing at the moment. We're being very reactive rather than proactive.
Absolutely, absolutely. And that tends to be the kind of state of things. People don't really get activated until after the fact, which is a problem. We find in government generally it's just quite slow. So talking of government, last year the government announced a £326 million investment in healthcare focused research and development. And you also discuss in the book that there's a $1 trillion potential in the bioeconomy. Where do you think, the UK should be focusing on, becoming a leader in science? I think something that we already are, but how do we best invest in UK
Yeah.
science?
Well, actually, I think it's a multi-trillion-dollar economy, right? I think this is going to be the biggest thing that humankind's ever, the most important and consequential technology we've ever invented, right? Which is basically turning biology into a predictive engineering material which becomes infrastructure, and in the same way that steel, when it became kind of commercialized on a massive scale, after Bessemer had reduced the cost of steel production by tenfold, it had geopolitical consequences, and biology, or generative biology as a technology, will also have geopolitical consequences. So whoever is the leader in this field, literally owns it and controls it, will own and control the future. Now, the UK and the US are both incredibly well positioned to lead. I saw a chart the other day of the number of science Nobel Prizes, and England and America were way at the top of that, right? And the UK, being such a tiny country, is obviously disproportionately represented in terms of its creative genius, right? So it is one of the things that the UK does best, but it's one of the things that gets least investment, right? So I would say that a government with imagination and foresight would be ploughing significant resources into ensuring that Britain attains the pole position, hopefully in conjunction with the US, and works together with the US to ensure that together they could lever each other's specific talent and capabilities. And obviously, the UK historically has always been the home of invention, and in particular in the area of molecular genetics. I mean, my old laboratory, the MRC Laboratory of Molecular Biology in Cambridge, has produced, I think at least 15 or 16 Nobel Prize winners, one of which was my PhD supervisor, Cesar Milstein, right? So, it's not by chance that we're producing so many Nobel Prize winners, and it would be a huge oversight and mistake of historic proportions if the UK didn't capitalize on that extraordinary resource and build upon it, because it's something that we do uniquely in the UK. I don't know why that is, and that's a whole nother field of exploration as to why, we've been so successful in that field and so creative. But we are. It's a simple fact. It's what we do best, right? And I remember at school, when I said to my teacher, what should I do? And he said, do what you do best. And actually, there's some truth in that, right? And it is what we do best. We're really good at science. In particular, we're really good at molecular biology. So we need to invest in it.
Absolutely. And you talk a lot in your book about DNA engineering and biology becoming infrastructure. And, from my viewpoint, I feel like infrastructure and engineering are definitely the future of work. But do you think that more people need to consider a career in science, and how possible is it to pivot into it? Is it something that you kind of have to have decided on at school, or should we be creating more pathways into this industry?
I think as time goes by, and AI's role becomes more and more predominant, the only real thing that differentiates us from machines, and in particular AI, is imagination, right? And to be a good scientist, you need to have a great imagination. If I'm really honest with you, when I was at school, I was by no means an obvious scientist, right? I mean, that's partially because I was pretty lazy and wild as a child, more interested in playing in rock bands and so on and so forth. But what I was naturally good at was English and history, right? I was never a natural scientist. But what I did have was a great imagination, right? And I think it's my imagination rather than my intrinsic scientific capability, because I'm very impatient when it comes to doing actual experiments. Some people are more patient than me and better suited to being in a lab. But what I have personally is an imagination, and I think there's a place for both types of scientists: those who are actually really good at doing experiments and designing experiments, and people like me who have a sort of bigger picture view and a creative, imaginative view. I mean, obviously, both experimentalists and non-experimentalists can have imagination. Ideally, you'd have both, right? But in my particular case, I've got more of the imagination and vision. And I think that's something that anybody can have, whether or not they've got a specific scientific background or not. And I think all of us can learn the basics. Uh, I think anybody can read my book, for example, and by the end of it, understand the field of generative biology pretty well, right? And once you do, you can have an opinion, you can have a point of view, and you could actually say, well, actually, look, I don't understand the details of this, but I think we could use this technology in this way, and this way, and that's what we should be doing, right? So I think there's definitely room for strategists who can deploy this technology. You don't need to understand what's under the bonnet in order to drive a car, for example, right?
That's a really good point. And talking about your company, Genyro, did I say it right
Yeah,
that time?
you did.
You obviously you mentioned you entered into a kind of collaboration with Sidewinder, which came from Caltech. We've seen a lot of world-class companies launch from university incubators, particularly in the science and tech space. Is this the future for innovative startups? And is this one way of answering the question that many recent UK graduates and prospective students are asking, whether university is still a viable path? Whilst it might not be able to secure a job, maybe, it's a route into entrepreneurship. Is this what maybe university should be for?
Well, interesting question. I think the good thing about universities, and I'm talking just about science now, right, is that it enables science to be done for science's sake without having direct commercial utility, right? And as it turns out, most of the important discoveries have happened in that way. The guy who first joined two nucleotides together to make a dinucleotide, which is the first synthetic piece of DNA. A guy called Professor Todd in Cambridge didn't do it because interested in, writing genomes, and he was motivated from by something completely different, which is color, dyes and coloration in insects, actually, right? And CRISPR, the gene editing technology, was discovered not because, the guy who discovered it was looking to develop a gene editing system for humans to correct inherited diseases, but he was just interested in how microorganisms were able to survive in these salt marshes in Alicante in Spain. It's pure curiosity driven research. But because of the way nature's constructed, it turns out that most species contain kind of earth secrets, to quote Thomas Hardy's poem. And those earth secrets contain incredibly valuable nuggets and insights for us about the world that we can then use to make the world a better place for us, right? So that's why curiosity-driven research is so important, and why universities have to exist in perpetuity. But can they also be incubators for companies? Yes. And I think the UK is definitely becoming much better at that. And I saw recently a white paper the government produced on synthetic biology, and clearly it's onto that. There is a realization of its importance, and I commend the government for producing that report. But I think the report has to be followed by tremendous investment, not just a small amount of investment, incremental investment, but serious investment. And if we do that now and invest in synthetic biology, we could become, in the UK as well as the US, a world leader in this field. But we'll get behind pretty quickly, right? So this has to happen in a timely manner. And really, if the UK doesn't do that, it will be left behind. So this is almost like a one in a lifetime opportunity. It's like Carnegie seeing the opportunity to commercialize steel once Bessemer reduced the cost, and obviously becoming a billionaire in the process, and and changing history, right? And we have that sort of Carnegie opportunity in front of us right here, right now. It's just sitting there, and whether or not the government chooses to run with that is going to be a matter of historical consequence.
And just like slightly on that, in 2024, 2025, we spent £205 billion on the NHS. Do you think a good chunk of that should be going more into R&D so that we can then bring that bill down?
Well, I have specific views on that, and I gave a talk at the Royal College of Physicians, some time ago on this exact topic, that, the NHS is an incredible organization, and people in the UK take it for granted and are always very rapid to criticize it, right? But you come live in America, where I live, and there are people without insurance who can't afford to get ill, because you end up in hospital, you get a bill for $500,000 or more if you're lucky, right? It's usually more than that, right? For just relatively minor problems, right? So the NHS is an extraordinary organization, but at the same time, it isn't, as we develop more and more treatments, uh, we'll end up using the entire GDP on the NHS, and that clearly isn't practical. So the question is, how can we have an NHS and treat diseases with the latest drugs and afford them? And I think the way to do that is for the government to actually develop drugs, right? To actually aggressively invest in biotechnology companies and biosimilar companies, and negotiate deals that, by means of their investment, they're able to obtain drugs at cost when they get to market. And that way, the NHS will be able to remove the components of its costs related to paying for drugs from its budget. And obviously, that will have a tremendous impact on cutting costs. If we don't do that, it's hard to see how the NHS is ever going to be sustainable in the long run. Obviously, as people's awareness of the need for defense goes up, some of that budget might be taken away from the NHS, right? And in a way, the only reason that the NHS has been able to exist is because that money wasn't going into defense because of NATO and so on and so forth, right? So it may be that the UK government is forced to rethink, all of this money that's being ploughed into paying for drugs, and will have to have a long-term solution to reducing its drug bill, right? So I think that that's a way in which thoughtful investment into the future can definitely build a future where the amount of money that's being spent on paying for drugs can be dramatically reduced, and therefore make the NHS a viable system for the future.
I think that's such a brilliant idea. And like you say, it seems so simple, but it's something we should obviously be doing, that everything we research, we should get like first refusal, or at least it should be being used by the NHS and supplied to the NHS. I think that's fantastic. And just finally, before you go, I know you're super busy and I'm so grateful. In your book, you write that the common misconception about natural selection is that every feature of a biological structure has been optimized. And you point to things like the human foot, which you say has 26 bones, not for adaptive reasons, but because it was once adaptive in a setting. Essentially that, we've at one point or another, it was useful, but it's not anymore. And you say, our feet function despite of the bones, not because of them. Do you think that if we are able to self-engineer our bodies based on what we need them to be now, is this peak natural selection, or is there a danger that we kind of eliminate the things for tomorrow that we don't know we need? You said that the more engineerable a synthetic species becomes, the more brittle it is, likely to be in the face of environmental variability and likely to be less resilient. So how do we square that circle of engineering based on what we need today and making sure that we're resilient for the future?
Yeah, well, even Darwin himself, was very clear that not every aspect of nature had been selected, right? That a lot of things just kind of, you know, went along with everything else because everything's interconnected, right? And it's also the case that everything today was built incrementally on everything that came before, right? So, the aeroplane has to stay in the air. You can never kind of go back to the drawing board and redesign systems using evolution, right? And because of that, there's a lot of, a lot of anachronisms in the designs of living things, and convoluted pathways and just strange idiosyncrasies that don't really contribute to function, right? And in many ways, one can think of those as being the causes of some diseases, right? Now, yes, there are some obvious poor design features in the human body, and perhaps if we, had been the designers ourselves, we might have designed them very differently. The human foot, as you correctly mentioned, has a lot of bones in it, right? Which it doesn't particularly make for a mechanically efficient foot. We'd be far better off having our foot designed like that of an ostrich, right? We'd certainly be able to run a lot faster and wouldn't end up with broken ankles and sprained ankles and so on and so forth, right? Should we ever try and redesign ourselves is a totally different question. And to be really clear, in my book, I am not advocating that we start to redesign ourselves, right? In fact, I'm super cautious about even editing ourselves, in incremental ways at the germline heritable level, right? But one has to have open eyes and think that in the future, it's quite likely, I imagine, that will be on the agenda, right? And therefore, we need to think about that proactively way ahead of time, even centuries ahead of time, right? Although it may not even be that long before people contemplate doing that. So the answer to your question, though, was you asked a very specific question, is that if we try to redesign ourselves, could we inadvertently remove features that might have been useful had we kept them, right? But of course, if we can redesign them, we can continuously redesign them and change them in perpetuity any which way we like, right? So I don't think in that case it would be relevant unless there was some catastrophic event, like a killer bacterial infection or whatever, which just wiped us out. And that happened because we had made specific changes, which made us brittle and vulnerable in the way that you stated, right? So I guess the answer the short answer is yes, but it's a bit, more complex in a sense, right? But as I said, I'm not advocating for rewriting or re-engineering human nature. However, I am kind of alerting folks to the fact that eventually we will be able to potentially redesign the human genome and to rebuild it. Of course, there's always the issue of the degree of computability of living things, right? So we know that it's not just genomes that control the nature of things, it's development, learning, culture, epigenetics, even the microorganisms that live on and inside us that can control the way genes are switched on and off, right? So I like to think of what I call the informiome rather than the genome. The informiome is all of the different layers of information that make us what we are, and really to predict the effects on the nature of a living thing, we need to have the complete set of information at every level, which invariably we will never have, right? So our computations and predictions must by necessity always be imperfect. And therefore, one could argue that if you can't precisely predict the consequences of changes, would it ever be ethical to make them? Which is why the barrier to engineering the human genome is so high.
Well, Adrian, thank you so much for joining me today. That was an absolutely fascinating conversation. And everyone, please do check out his book on the future of species, out now.
Jamila, thank you for having me on. It's been such a great pleasure talking to you today.
Thank you. You too.